Our final chapter this semester deals with energy. Energy takes on two general forms: energy of motion, called kinetic energy, and energy of position, called potential energy. In these two general forms, there are many more specific forms like thermal energy, a form of kinetic energy from the movement of particles; mechanical energy, the more familiar form of kinetic energy in macroscopic objects; and electrical energy, a kinetic energy that depends on the speed of electrons; and even sound energy, that's energy transmitted through the waves of matter. Technically, the wave is both kinetic and potential as it displaces the particle in a medium, but we'll categorize it like that for now. Potential energy is most familiar as gravitational potential. I raise a ball, it has potential energy. I raise it higher, it has more. But electrostatic energy is also important. If I put two negative charges near each other, they repel. If I put them closer, they repel more. If I put negative charges all through my hair, I look like Einstein. Of course, in chemistry, we also care a lot about energy that's stored in bonds. This is a sort of potential energy as well, at least conceivable as bonds stabilized by nuclei having appropriate distances apart, and bonds having optimal overlap. Not all of the potential energy in these chemical systems are available. The chemical energy depends mostly on the available or free energy that can be changed in the course of a reaction. The types of energy that are highlighted in red are what we'll focus on in chemistry. Two basic rules of energy are that energy can change from one form to another, and that whenever they do, no energy is ever lost. The conversion and retention of energy make up the first law of thermodynamics, the study of the transfer of energy. These diagrams, called reaction coordinate diagrams, show the progress of a reaction starting on the left of the graph and moving toward the right. The first flat spot represents a property of the reactants, usually heat or free energy, an important concept that we'll talk about later. The final platform represents the same property of the products, and the line between traces how that property changes as the reactants are converted to products. One of the main conversions we observe in chemical reactions is a change in heat energy. Some reactions are exothermic, which means that energy stored in the bonds of the molecule are converted to heat. Other reactions that are endothermic use heat from the environment to store energy in bonds. It's tempting to hear heat and think temperature. The differences aren't well defined in common discourse, but heat and temperature are both measures of kinetic energy that have different nuances. Temperature is a measure of average kinetic energy over an entire molecule, no matter what it is or how big it is. Heat, on the other hand, is a total over the whole material, so it matters how much there is. And because different materials can carry heat differently, heat also depends on the type of material. Heat's an effective measure for us as chemists because it's related to the other forms of energy we may encounter in chemistry, and even includes chemical potential. Even though heat is not the same as temperature, the concepts are closely related. As more and more heat is added to a sample of constant mass and constant phase, like it's always liquid for example, the temperature goes up linearly, or at least nearly linearly. This graph shows us the relationship between added heat, which is often indicated with the letter Q and measured in joules, and temperature, which could either be degrees Celsius or Kelvin, here it's Celsius. The slope of the graph is constant, around 41.84 joules per degree Celsius. Strictly speaking, this line shouldn't be completely constant. The heat gained by a given amount of substance per an increase in temperature, called specific heat, actually increases slightly with temperature because higher temperatures allow molecules to gain kinetic energy not just from moving, like in lower temperatures, but also from vibrating within the molecule and rotating the molecule. But for the purposes of this class, we can think of specific heat as a constant for a substance. Again, the slope of this line is pretty close to specific heat, but it doesn't actually give specific heat, which has units of energy per mass change in temperature. It only gives energy per change in temperature, here joules per degree Celsius. This is known as the heat capacity, a measurement of an entire system. Specific heats, defined for individual homogeneous substances, are given in joules per gram degree Celsius. What about the data shown do you think would allow you to calculate the specific heat for water? If you aren't sure, look up the actual value for the specific heat of water to see if that guides your answer. The specific heat of water would be the heat capacity of this entire system given by the 41.84 joules per degree Celsius slope of the graph over the 10.0 grams of water in the system. The result is 4.18 joules per gram degree Celsius, which should match up with the specific heat of water. Specific heat can be used as a conversion factor between mass and temperature and energy. Because it's a complex unit, I often see students try to use it as a formula. Don't do that. When you are always careful about how a calculation will actually change the units using dimensional analysis, you'll always end up with an appropriate unit. Specific heat is very much a derived unit. The SI form is joules per gram degree Kelvin, but since the temperature change is what we're actually going to measure for temperature, both Kelvin and Celsius give us the same result. Joules are the SI unit for energy, which goes on top of specific heat, and they're derived from other derived units, which you can see in the notes on the bottom. The unit calorie is another unit for energy. It's an empirical unit based on water-specific heat. We don't use it a lot in chemistry, we usually use joules, but it's really convenient for biological systems. It's worth noting that the capital C calorie that's shown up in nutrition labels is technically a kilocalorie, while the lowercase c calorie is the calorie that's worth just over 4 joules. Specific heat is a really useful constant for materials, as it allows us to use an amount of a substance and a temperature change to measure the actual energy of a system, or the change in actual energy of a system, which is more closely related to the chemical dynamics of that system than the temperature is. Let's do a few examples. First, let's figure out how much energy it takes to raise 1 liter of water from 25 degrees Celsius to 100 degrees Celsius to take some potatoes, boil them, mash them, stick them in a stew. The actual form for using specific heat to find heat energy is to take the specific heat, typically in joules per gram degree Celsius, then multiply it by mass to cancel out grams, and then multiply it by the change in temperature, which should be final temperature minus initial temperature, to cancel out the temperature unit. Make sure you convince yourself that the units that are left over at the end of that calculation are joules. So that's the setup. But we're getting to a point in the semester that we should be able to convert between common measurements to make sure we can use them. So we'll do a little bit of review here too. The problem gives us a volume of water, what we're likely to measure, but specific heat requires a mass. See if you can convert the liters into grams. Hopefully you know the density of water at least to one significant figure by now. It's 1 gram per milliliter, but you could always look it up too. So we can convert liters to milliliters and milliliters to grams. That result in 1,000 grams to one significant figure. Now we just need to plug this into the setup. See if you can do that and find the amount of energy in joules it takes to boil the water. For reference, the specific heat of water is given in the last slide, again here in the definition of calorie, and also, on the internet. We only need to take the specific heat of water, 4.184 joules per gram degree Celsius, and then we multiply it by 1,000 grams to cancel out the grams unit, and then by 100 minus 25 to cancel out the temperature unit. That's our difference in temperature. Our result to one significant figure is 3 times 10 to the 5th joules, or 300 kilojoules. When we're subtracting temperatures, it's important to remember that we always take the final temperature minus the initial temperature, regardless of which is larger. If the final temperature is lower, we'll end up with a negative change in temperature, and therefore a negative energy. That's fine and actually important. A negative energy means that energy is being released from the system instead of being absorbed. Now it's your turn to do the same type of calculation with oil. So we're all using the same values. Cooking oil has a density of 0.918 grams per milliliter and a specific heat of 2.0 joules per gram degree Celsius. Take those and find me some heat. Just like before, we need a mass to convert with specific heat, but we're given a volume. Using the density of cooking oil, we can find that the mass is about 900 grams. I'm keeping the leftover significant figures for my calculation, even though I know I'm going to eventually need to round off at the end. The final setup is just specific heat times mass times change in temperature. Again, being careful to have the final temperature minus the initial temperature, for a result of 3 times 10 to the 5th.
joules. Interestingly, we raised oil to a much higher temperature, but it doesn't have much different heat due to its lower specific heat capacity. Oil is actually used in cooking for 3 reasons. It takes less energy to heat up, like we just saw, but it can also cook at higher temperatures because of its higher boiling point, or smoke point, which is actually what limits oils in many cases. And finally, because oil doesn't seep into the foods and make them mushy like water. It seeps into foods and makes them full of saturated fats. An air fryer or a convection oven does all of these things better. A small layer of oil on the surface of foods and the air around it can be heated up much faster than oil or water and with less energy. The oil on the surface of foods can get up to 200 degrees Celsius or more, which facilitates the Maillard reactions that cross-link carbohydrates and proteins and make the surface of the food crispy and delicious. And neither oil nor water soak in as much since air is the main medium. I'm so hungry right now. We can take advantage of what we know about specific heat and heat capacity to measure the types of heats that are produced by reaction, which sometimes we actually call heat of reaction, using instruments known as calorimeters. Calorimeters give a reaction chamber that's placed in a surrounding solution that can soak up heat from that reaction. The solution is usually water. Water has a high and well-known heat capacity, so if the amount of water is known and the change in temperature can be measured, we can find that heat of reaction, that is, the energy it produces or consumes. The water solution and the reaction need to be isolated from everything else that's outside, so energy isn't gained or lost except due to the reaction. If that system is well insulated, then the heat that is gained or lost by the system will be the opposite of what we observe in its surroundings. The temperature change in the water will be the opposite of what happened in the system. We can calculate that using the specific heat of water, the mass of water that's in the system, and the change in temperature. Note carefully that the sign changes between the system and the surroundings. If temperature is increasing in the surroundings, we get a positive Q of surroundings but a negative Q in the system. The case in exothermic systems, which is shown in the calorimeter on the left. If the temperature is decreasing in the surroundings, the Q is negative there, but positive in the system, an endothermic system, shown in the top right. When we think about our reaction coordinate diagrams in terms of heat, that means that our exothermic reactions are defined with negative Q values, and our endothermic reactions are defined with positive Q values. Calorimeters can be as simple as an insulated cup, but the best calorimeters are highly precise pieces of equipment, where not only the specific heat of water is carefully measured, but the heat capacity of all material within the insulation are carefully documented and used for calculations as well. Often the reactions measured are combustion reactions, and the reaction is forced to completion by a large excess of oxygen. If you perform this in a physical chemistry class with Vanderwood, you'll use a bomb calorimeter like the one that's shown, that is filled with 10 atmospheres of oxygen pressure and ignited to measure the heat of combustion for a material. Calorimeters can also be used to measure specific heat of an object. To do this, an object of known mass is heated to a known temperature and dropped into a calorimeter containing water at a known temperature. So the changes in temperature can be known easily, as can the mass. The heat from the object will move into the water until the temperature of the object and the temperature of the water are the same. The actual equation is just 2 calculations of energy from specific heat, mass, and temperature change, since we know that the energy going out of the object has to be the same energy that's absorbed by the water. On the left, the specific heat of the object isn't known, but the mass and change in temperature are. On the right, the heat absorbed by the water must be the opposite of the heat released by the object, so we can use water's specific heat, mass, and temperature to find the energy given by that side. Solving for specific heat allows us to determine the specific heat for the metal.